If you haven't done so yet, please pause the video and attempt to solve the question on your own before moving on. We can begin to solve the question by drawing a simple picture that represents the information being described. So we have the bullet compressed against a spring with an initial velocity of 0 meters per second, and then it is released, so the spring becomes relaxed and the bullet is launched with some final velocity. Now, because of the presence of friction, we have to use a special version of the work energy theorem. So this is an equation that's presented in the chapter. You're going to use this equation whenever friction is present and you're trying to use an energy approach to solving the question. WNC is going to be the work done by friction, which we know can be represented by the frictional force multiplied by a distance multiplied by the cosine of an angle. Now, as the bullet is launched forward, its displacement would be pointing to the right. The frictional force would be pointing against the motion. We can see that the angle between the frictional force and the displacement would be 180 degrees. So we're going to be plugging in 180 degrees for the angle there. On the right side of the equation, the gravitational potential energy plays no role in this question because the bullet is not moving up or down from where it was launched, so we can eliminate the gravitational potential energy. Also, the initial kinetic energy of the bullet can be eliminated from the equation because the bullet is initially at rest, and any object at rest would not have any kinetic energy. In the final scenario, we can see that the spring was relaxed, so that means that the spring potential energy final will be 0, so that gets eliminated from the equation. And so we can greatly simplify the formula. Now, we recall that kinetic energy would be equal to 1/2 times the mass of the bullet times the final velocity squared, and then the spring potential energy is 1/2 times the spring constant times the displacement of the spring squared. Now, of course, we're trying to solve this for the final velocity of the bullet, so we can actually multiply both sides of the equation by 2. And when you distribute that 2 to the 1/2 here and to the 1/2 there, it'll cancel out those 1/2s because 1/2 times 2 is 1. We could then add the k delta x squared term to both sides so that we move it over to the left. We could then divide both sides of the equation by the mass m. And then finally we can take the square root of both sides, and that way the right side becomes VF. Now, we've cleaned up the workspace and we're getting ready to plug in all the known values. K was given to us directly and in standard units. Delta x is the amount that the spring was compressed. We're going to have to multiply that by 10 to the minus 2 to convert it into meters. The kinetic frictional force was given to us in standard units. S is the distance that the frictional force is applied. That's just going to be the total length of the barrel of the gun. That needs to be multiplied by 10 to the minus 2 to convert it into standard unit as well. The mass was given in grams, so that needs to be multiplied by 10 to the minus 3 to convert it into kilograms. And when you plug that all into your calculator, you should get an approximate value of 1.4 meters per second for the final speed that the bullet has as it leaves the barrel of the gun. Thanks for taking the time to watch the video. If you'd like to, please subscribe to the channel so you could stay tuned for additional videos. Also, you are welcome to send in your own question to the email address on the screen.